Hello and welcome to ENGR 320 Thermodynamics Recitation on Chapter 3. I am Dr. Krishna Pakala and I'll be helping you solve few problems from Chapter 3 to better understand the lectures we covered. So in Chapter 3, the major things we covered are the property diagrams for phase change processes. For example, here I show a TV diagram, and depending on a particular temperature or a pressure or a combination of these values, we can say whether our fluid is in the compressed liquid region or in the saturated region or in the superheated region. And also understanding of this process will then help us for any additional properties we want to find using the property tables. And also we learned the compressibility factor, which can help us identify the deviation of a particular fluid from the ideal gas. Let's look at a problem. So problem 327, we are asked that to complete a table. And here the fluid is refrigerant 134A and the units are in SI system. So for example, in the first row, we are given a temperature and a pressure, and we are asked to identify the phase and also find the specific volume. So the way we do that is, one way is you go to table A11, which is the temperature table for refrigerant 134A, and you find that for minus 12 degrees C, the pressure given, which is 320 kilopascals, is greater than the saturation pressure at the same temperature, which would mean that the phase is a compressed liquid. Another way to look at the same thing is if you were to go to table A12 and look at the pressure for 320 kilopascals, you would find the saturation temperature, and you would see that the temperature which you are given, which is minus 12, is less than the Tsat, which would also imply that the phase under consideration is a compressed liquid. Once you decide on this, then you can quickly find the specific volume at minus 12C from table A11. Since pressure doesn't really affect the specific volume calculation. Then in part B, which is the second row, we are given a temperature and a specific volume. First, let's try to identify the phase. We see that for this temperature from table A11, the specific volume is between the fluid temp specific volume and also the gaseous specific volume, which would mean that it is a saturated mixture. So if you were to go to the saturated table for the corresponding temperature, you can pick the corresponding pressure in kilopascals. And for part C, we are given, which is third row in the problem, you are given a pressure and you are given that the phase is saturated vapor. So you go to table A12 and find the temperature and the corresponding specific volume. And in part D, we are asked to identify the phase and also find the specific volume. So here you are given a combination of temperature and pressure. So if you can go to table A11, you would see that the pressure you are given is less than the Psat at a particular temperature of 60 degrees C, which would mean that you are dealing with superheated vapor. Or another way to look at the same is go to table A12, look at the pressure and find out the corresponding Tsat, and you see that the Tsat at this pressure is less than the temperature given. So that would also mean that we are in the superheated vapor zone. Now let's look at problem 340E. You're given that 1 pound mass of water fills a container whose volume is 2 cubic feet. The pressure in the container is 100 psi absolute, and you're asked to calculate the total internal energy and enthalpy in the container. So first we would like to know the state of this fluid, and in our case it is water, and the pressure given to be 100 psi A, and the volume of the container is to be 2 cubic feet. So first we need to convert the volume given into a specific volume, where we divide the total volume with the mass of the fluid, so which would give us 2 cubic feet per pound mass. So from table A5E, since now we are dealing with English units, at the above specific value and the pressure of 100 psi A, we observe that this value is less than the Vg but greater than Vf, which would mean that we are dealing with a saturated mixture. So then the way we find the total internal energy and the enthalpy is by first finding the X value, which is nothing but V minus Vf over Vfg. So which we can quickly find from the table, and it would be 0.449. Then you can substitute X and also the internal energy for the fluid and UFG from the table, and you determine U, which is the internal energy per unit mass, and H, enthalpy per unit mass. Then the total internal energy, big U, will be mass times the internal energy per unit mass. So this way you would get the total internal energy and the total enthalpy. In this problem, we're told that 100 kg of refrigerant 134A at 200 kilopascals are contained in a piston cylinder device whose volume is 12.322 cubic meter. The piston is now moved until the volume is one-half its original size. This is done such that the pressure of the refrigerant does not change. So we are dealing with constant pressure process or isobaric process. And we are asked to determine the final temperature and the change in the total internal energy of the refrigerant. So let's identify the state 1, which is shown on the PV diagram. So we have a refrigerant whose mass is 100 kilograms and a pressure of 200 kilopascals, and we know the total volume. And we can find the specific volume, and we observe that at a particular pressure of 200 kilopascals from table A12, the specific volume in the problem is greater than the specific volume of the gas at the same pressure, which would mean that we are in the superheated vapor region. That's why we are right off that line there on the PV diagram. So from table A13, which is for the superheated state, we get the pressure, and the specific volume will give us this internal energy at state 1. And at state 2, your pressure is again a constant, and the specific volume now reduces to half of the previous original state. So we observe that this value is between Vf and Vg, which would mean that now we are dealing with a saturated refrigerant, which is shown on this PV diagram. So we can obtain the temperature at T2 at this state from table A12. Similarly, now if we are asked to find the internal energy, then first we need to find X2, since it is a saturated mixture, and we can find that easily, and then we can determine the internal energy at state 2, and the change between the two states will give us the total change in the internal energy, and the total change would then be delta big U, which is mass times delta U. Now in this problem, we're looking at a rigid container which contains an ideal gas at 1227 degrees C and 200 kilopascals gauge. The gas is cooled until the gas pressure reaches 50 kilopascals, and also we are given that the atmospheric pressure is 100 kilopascals, and we are asked to determine the final temperature of the gas. So in this process, the energy is leaving the system, and T is 1227 degrees C, and we are given the atmospheric and the pressure gauge. So since it's a rigid container, we can consider this as a constant specific volume process. So from ideal gas law, we can determine that P1 over T1 should be equal to P2 over T2. And remember, in ideal gas, the units of pressure and temperature have to be in absolute scale. So we can convert the pressure from the gauge to absolute using the formula shown. P absolute is P gauge plus P atmosphere. And also we need to convert the temperature from Celsius to Kelvin. So once we do the math there, we end up getting T2 to be 750 Kelvin, or you can convert it back to Celsius and you would get 477 degrees C. In problem 94E, we are given that a saturated water vapor at 400 Fahrenheit is heated at constant pressure until its volume has doubled. And we are asked to determine the final temperature using the ideal gas equation of state, the compressibility charts, and the steam tables. So we're going to look at the final temperature using three different ways. So first let's look at using the ideal gas equation. And we know from the problem that it's a constant pressure process or isobaric process. So at state 1, we have a saturated water vapor at a temperature of 400 F, and P1 is Psat, and let's call the specific volume as V, and at state 2, it's the same pressure, however, the specific volume is now doubled. So for a constant P process, we can determine a relationship between temperature and specific volume as shown, and we can determine T2 at this final state. And in part B, we have to use the compressibility charts. So we have to now deviate from the ideal gas behavior. So first let's try to find P1, and which will be equal to P2, which will be Psat at that temperature, which is 400 F. And we can determine this from table A4E. And similarly, we can find the specific volume at that combination of pressure and temperature, and then at state 2 it is twice of this value. And then from table A1E we can determine the gas constant, the T critical and P critical. So for state 2, PR2, which is the reduced pressure, will be P2 over P critical, and the pseudo reduced specific volume would be as shown, and using these two values and using figure A15 we can determine the compressibility factor, which is 0.985. So from there we can find T2, which happens to be 1571 Rankine. And in part C, we're asked to use the steam tables. Now if you observe, our pressure is 247.26 psi absolute, and you have a specific volume which is 3.7278 cubic feet per pound mass, and we are asked to find T2 using this method. If you look at table A6E, we find that these numbers do not exactly are represented in the tables. So we have to do an interpolation. Since we are talking about two different pressure, for a constant pressure we have specific volume and temperature as the variables, we have to make sure that we come up with a strategy to find for a fixed pressure what would be the specific volume and what would be the corresponding temperature. The way you do that is you first find the pressure lying between two values from the table, and it happens to be 225 psi A and 250 psi A for our case, and find the specific volumes at those ranges and then the corresponding temperatures. Similarly, find another range which would be greater than the specific volume given in the problem, which happens to be 225 psi, 250 at the same pressure. However, the temperature now is 1200 Fahrenheit and 1200 Fahrenheit for pair 2 of our selection. So now the way we do the double interpolation is, for pair 1, we have a fixed T and we have a pressure which is 247.26. Now let's try to find what would be the specific volume for the pressure which is 247.26. The way we can do this is by simple linear interpolation, and the formula is shown there, and you would end up with a specific volume which is 3.4827 cubic feet per pound mass. Again, we do a similar procedure for pair 2. Now we have a different fixed T which is 1200 Fahrenheit and the same pressure which is 247.26. We find what would be V at this, or the specific volume. So we end up with 3.9777 cubic feet per pound mass. So now what we have essentially done is, for a fixed P, we have determined this range of specific values and the range of temperatures. And we observe that the choice of our pairs so happened that the specific volume which we have in the problem, which is 3.7278 cubic feet per pound mass, lies between the two values shown in this double interpolation. So that would mean that if we pick the V and T combination for a fixed P, we should be able to determine T2. And as shown there, we determine that it's about 1559 Rankine or 1099 Fahrenheit, which would be our T at the state 2. And this makes sense because it has to be between 1000 and 1200. Now let's look at another problem. Here we are given a tank which contains helium, an ideal gas, at 77 degrees centigrade and 110 kilopascal gauge. The helium is heated in a process by heat transfer from surroundings such that the helium reaches a final equilibrium state at 300 C. And you're asked to determine the final gauge pressure of the helium. And you're asked to assume atmospheric pressure, which is 100 kilopascals. For this process, we can make the assumption of constant specific volume. And for an ideal gas, we have P over T equals constant, or P1 over T1 equals P2 over T2. So we can determine P2, but remember, you need to have both your pressure and temperature in absolute scale, which is what we have done there, and then you would end up with 343.8 kilopascals at state 2. However, you're asked to determine this pressure in gauge. So the way you do that is, the pressure which you got, subtract the absolute or the atmospheric pressure, and you would end up with 243.8 kilopascals, which is the gauge pressure at state 2.